All right, let's get started. Welcome to the statistics seminar. And it's my great pleasure to introduce Yuekai from Stanford University. He's a PhD student in the Institute for Computational and Mathematical Engineering. And he's supervised by Michael Saunders, who's in the Operations Research Department, and Jonathan Taylor in the Statistics Department. So, consistent with that, he has diverse interests. He is published in optimization, machine learning, and high-dimensional statistics. And today he's going to talk about some of his work in sparse regression.
Thank you, Ambush, for the introduction, and well, thank you all for coming, and thank you all for the invitation. So, as the title alludes, this will be kind of a two-part talk. We'll talk about two aspects of the sparse regression problem. One is about estimation, and the second is going to be about inference. And this is joint work with my good friend Jason Lee and my advisor Jonathan Taylor. Okay, so this is a job talk, I'm given the way I'm dressed. And so I'm going to kind of set the context of this talk within the broader framework of my work. So, as Ambush mentioned, I work in statistics and more computational side of things. So in statistics, mainly high-dimensional, in the high-dimensional setting. So I've looked at consistency properties of regularized M estimators, and well, the second part you're about to hear, so I'll hold off on a description of that. Like I said, I'm also interested in computing. So what am I interested in computing? At the very beginning, it was methods for optimization. I mean, a lot of statistical estimation today relies on optimization, and so algorithms for optimization are in some sense the core of enabling us to do estimation of a lot of these high-dimensional settings, if you will. And more recently, looking at distributed algorithms. So computational techniques that are very useful when your data has to be distributed across different machines, and looking at how to minimize communication, which is the dominant computational process. And I'll talk a little bit more about this. This is the first part of the talk. And finally, I've done some applications with respect to biology and also machine learning, so recommender systems in particular. Okay, so the things highlighted in blue are the two things I'm going to talk about today. One from statistics, one from computation, just to give you a flavor of the stuff I do. Okay. So to talk about both of these things, I'm going to have a very concrete setting. I'm going to set them within the context of the sparse regression problem. I'm sure a lot of you are familiar with it, but just to kind of set up notation and whatnot, we're going to go through it very quickly. What is the sparse regression problem? You are given a design matrix X and the vector of responses Y, and you essentially want to find a small subset of the columns of this matrix to express the responses in. And the small subset is where the sparsity comes in. This problem, we know how to do very well. We have very efficient estimators, and we also know how to compute these estimators, at least in a shared memory setting. There are a lot of algorithms for doing so. Despite this large body of work, if you will, there are, I think, two challenges that, at least I work at. They're not the only challenges, but two challenges that this talk will focus on. And the first is, can we do computation? Can we compute these estimators efficiently where the data is not stored centrally, but say distributed on more than one machine? That is the first challenge. And the second challenge is, notice everything that I've talked about concerns estimation. Can we do inference as statisticians? We would like to know a little bit more. Can we form confidence intervals for the coefficients, or do hypothesis tests? So this is what we're going to focus on in this talk. Okay? And the first part will be about how to do sparse regression in distributed setting. I'm going to begin with that. So what is the distributed setting? Okay, what do I mean by data distributed? So I consider my data as pairs, X and Y, predictors and responses, and I'm going to split the data by sample. So if you think about this matrix, X, and the vector responses Y, they're split row-wise, okay? So each machine will get a subset of the rows of X, split by sample. But this part of the talk, just to fix some notation, M will always be the number of machines, okay? The index K will index machines. So anytime you see a quantity denoted with a subscript K, that's a local quantity. That's a quantity on the K machine. And finally, capital N will be the total number of samples, and little n will be the number of samples per machine. Okay, and for simplicity, we're going to assume that the samples are split evenly, so every machine has little n samples. Okay, so here's the setting. And now let's think a little bit more about computation in this setting. Okay, when we do computing, there's really two costs, or at least main costs that are associated. One is what I just call computation. So this is the cost of actually crunching the numbers. Okay, this is measured in floating point operations. And traditionally, this is what we think of when we think of computational cost. When you say matrix multiplication, matrix multiplication is n cubed. It's n cubed forms. That's what they're talking about. There is a second cost that is coming more to the front. And this cost is communication, okay? It's the cost of shuffling data around so that they can be in the right places for the numbers to be crunched. Now, on a single machine, this is not a huge deal because everything is kind of vertically integrated. You got RAM, you got registers, you got cache, and then finally you got a processor. But in a distributed setting, this is kind of the dominant cost, okay? Because now, you might have to pass data instead from RAM to processor, you have to pass it over Ethernet. You may have to write it to hard disk in say MapReduce. That's how data is communicated. And so this is, in some sense, the dominant cost that we're going to worry about. And there's, in some sense, there's a parallel trend in terms of the energy of computing. So all I've said previously is wall time. But if you look at, say, the number of joules required to perform a computation, it also has a similar trend. It costs a lot more energy to pass data over a network than to just compute or do a plot. Okay. So the message is we want to minimize communication, we want to avoid communication. So what's wrong with what we know, with the standard algorithms that we know and use so well in shared memory settings? So, well, let's look at one of them, and let's look at the lasso. So, first thing we notice about the lasso is it's an optimization algorithm. Okay, it's the solution to an optimization problem. So in general, you're going to have to iterate to compute the lasso estimator. Now this by itself would not be so bad. This by itself wouldn't be so bad, except I have to communicate at every iteration. Why? The data is distributed. So to evaluate this part and its gradient of the objective function, I'm going to have to aggregate data from multiple machines. So I have to communicate every iteration. If I think about doing this, say in the context of a first order method, communicating every iteration, when for possibly hundreds of iterations, the cost is going to add up pretty quickly. Okay, the cost is going to add up pretty quickly. Now I'm thinking about this in the context of a first order algorithm. There are other algorithms for computing the lasso in this setting. Some of you might be thinking about ADMM. But in general, these algorithms have similar communication patterns. They're all iterative, and they all require you to communicate at every iteration. So the cost will add up. The cost will add up. Okay. So at this point, there are kind of two things we can do. The first thing is, can we think of an algorithm to solve the lasso? Let's keep the lasso. Think of an algorithm to solve it in a communicating, avoiding fashion. Okay, an algorithm that doesn't communicate so much. And this has led to a very long line of work that has been very fruitful, but this is not what we're going to do. Okay, what we're going to do is we're going to scrap the lasso, and we're going to cook a new estimator that is amendable to this distributed setting. That is what we're going to do. Okay. And the challenge we're going to set ourselves is, can we do this with only a single round of communication? We're going to single round of communication. I'm not going to keep you guys waiting, so this is exactly what we're going to do. So what's going to happen is each node will compute what I call a de-bias lasso estimator. Okay, and I'll justify what I mean by de-bias in the coming slides, why I call it de-bias. But essentially what it involves is you solve the lasso with only the local data. Okay, only the local data. These quantities all have a subscript k. And then what you're going to do is you're going to add a correction term to this lasso estimator. Again, this correction term only involves local quantities. No communication is required in this step. What's going to happen is then there's going to be a master node, and it's going to average all the iterates. Okay? And this is the only step that requires communication. You have to communicate each local estimate to the master node, and then the master node will average it. And finally, to get a sparse estimate, you're going to threshold this average. Okay? So the only step that requires communication is step 2. Single round of communication. This is what we're going to do. Now, for completeness, this correction term involves inverting a matrix, sort of inverting a matrix. And how exactly we're going to do this doesn't really matter. Okay, and here's one way to do this. In particular, we require this inverse to be good in an entry-wise L infinity sense. That's the first line here. Here's an example of a possible program to do this.
Well, can I ask a question? So if
Yes.
you go back to that last slide,
Yes.
so what you're doing is your beta hat K there, that's sparse, and now you're going to desparsify it in
Yes.
that usual sense. Okay, so you desparsify it, and now you combine this desparsified, and then you
And then you
sparsify it.
specify it again.
Yeah,
Yes, there's a.
are you still iterating somewhere?
Yeah, so to solve this last requires iteration,
So
but no
iteration.
communication, because this is only done in the local data.
But the second step only happens once, right?
Yeah, this is the step where you communicate. Yes. Step 2 is where you communicate. Any other questions on what I'm going to do? Okay. So, as I was saying, this correction term requires kind of this approximate inverse to the.
What's this HT? This thresholding some sort?
Yeah, it's hard threshold. I'll tell you exactly what it is, but you just set everything that's below a certain threshold to 0.
Sure. Okay.
That's it.
Thanks.
Okay. So I was saying you need to approximately invert this matrix data. Approximately invert this grand matrix. And this is one way of doing it. It's not particularly important in details. The two key takeaway points is yes, you can do this. It's an L1 regularized quadratic program. We know how to do this very well. And it's only done with respect to local data, so no communication is required to perform this step. There are other ways of doing this, but I won't go into the details. Feel free to ask me questions if you're curious.
So is this
Yes.
some sort of generalized inverse or something? I mean, it must be some sort of
You
a
can-
generalization of a generalized inverse or something.
You can consider it a generalized inverse because you kind of set this parameter to 0, and the only feasible point is the inverse. But it's a relaxation of the inverse. I'm allowing some slack in an L infinity. I'm allowing the inverse to be deviate from the identity, the product with the original matrix to deviate from the identity in entry-wise sense. And why is this so? It's because I require for my proof. Yeah. Yes. Okay. Any other questions about what I'm going to do? Yes, Johan.
Is this related to the Tom type of
Yes, there is some relationship. There is some relationship. You know, in particular, the constraints are very similar. Although the structure that the objective function is different. So they're trying to estimate a sparse matrix, so they penalize the sparsity. Here, I'm penalizing something that will turn out to be, will affect the variance of my d-bias estimate. I want the variance to be small. But the constraint is the same. Yes. Any other questions? Okay. So I alluded to this estimate I call the d-bias lasso. What exactly do I mean by the d-bias lasso? Well, to tell you a little bit more about bias, I need to set up the underlying statistical model. So here's the underlying statistical model. It's just the standard sparse linear model. Y is given by x times some sparse vector beta naught plus Gaussian noise. Okay, I'm going to assume that the x's are random and it has some covariance structure. But aside from that, I'm not going to make any assumptions. Oh, and S is the number of non-zero components of beta naught. Okay, so if you think back to what we did, essentially the main idea boils down to averaging. Okay, the main idea boils down to averaging. So the most naive thing you could do is just average a bunch of lassos. You could just simply have each node compute the lasso and just average all this stuff. Why does that not work? Okay, so here's I'm running a simulation here. On the y-axis, you see it's just error, so distance from your estimate to the truth, E2 north, squared, I think. And on the x-axis, I'm just growing the number of data points. Now I'm doing this, and it's the total number of data points, remember? I'm doing this in a fashion that's keeping the number of data points on each machine constant. So each machine always has 1,000 data points in this setup, and I'm just simply growing the number of machines. What I hope to see is that even though each machine doesn't get more data, I hope to see the effect of aggregating. I hope to see the error go down. But just averaging lassos, which is the blue line, error doesn't seem to be going down. You know, at 10,000 data points, I seem to be doing comparable to the error is about the same as at 2,000 data points. With 5 times as much data, I don't really see any difference. I don't really see any difference. Now, why is this? Why is this? If you think about what averaging is doing, averaging reduces variance, right? But if you have some systemic bias in the points that you're averaging, this is not going to go away if you average. So we need to find some way to get rid of the bias of the lasso. Oh, and why is the lasso biased? Because you're shrinking everything. You're putting a penalty. That's why everything's biased towards 0. So I need to find some way to undo this bias, okay? this is what I'm going to do. If you look at the optimality conditions of the lasso, you can wishfully, by wishfully I mean assume that this matrix in the middle is invertible. You can solve for the lasso estimator. And you can use an expression that essentially is the truth, beta naught, plus a term which I'm going to call variance. It's variance because if you consider the x is fixed, then epsilon is mean zero noise, so this term is mean zero. And the second term, which I'm going to call bias. What is the d-bias lasso? This is the expression I wrote down in the previous slide. Okay. By the optimality condition, this correction term is equivalent to, well, simply the other side of the optimality condition. But it's the same as this bias term. If you would squint and pretend that this beta hat k and sigma hat k inverse are the same. Okay? So what I'm literally doing is I'm just taking this expression and I'm adding back the bias term. This is what I mean by de-biasing the lasso. I'm just going to add it back. This is the intuition. This is the intuition. This derivation is non-rigorous. I'll give you a rigorous statement on the next slide. So this is the intuition behind the de-bias lasso. If you were to repeat this computation in rigorous fashion, this is what you would get. You would get that the de-bias lasso has the following form. Is the truth plus this familiar variance term plus this term is now the bias term. Okay, this term is now the bias term. If you do some math, you can show that the variance term is of lower order than the bias term. Okay, the variance term decays by 1/√10. The bias term decays by 1/n. So the intuition here is if I keep a sufficient number of data points on each machine, then the bias is negligible compared to the variance. I can neglect it. Okay, at least it's higher order. So this is kind of the intuition that we're going to proceed with. In order to make averaging succeed, I just need to make sure that each machine has a sufficient number of data points. Okay, and how big is enough? Well, it's n bigger than some constant times x squared log p. This is what's enough. So let's average it. Okay, and this is the expression for the average d-bias lasso. I simply stuck an average in front. You can prove a very similar type of result, except now the key difference is that notice that the variance term is dependent on the total number of data points instead of the number of data points on each machine. This is the effect that I want. I want this estimator to be taking advantage of the total number of data points, not just what's on each machine. Now the bias term still depends on the number of data points on each machine because averaging does not lead to bias, so it keeps it about the same magnitude. I simply have to ensure that the variance term is dominant, that it is the dominant term in the error. And like I said, I'm going to do this by keeping a sufficient number of data points on each machine, or not splitting the data too many ways. I'm not going to split the data across too many machines. If I split the data in so many ways, such that there's only one point each machine, you consider this is quite hopeless. Okay, I need to keep sufficient number of data points on each machine. I need to keep the total number of machines low. So if you do that, then you can derive an error bound, an L infinity error bound in particular. And this is just a simulation that kind of confirms this fact. Okay, so the setup is exactly the same as in the experiment, the simulation with just averaging lassos, except now I'm averaging d-bias lassos. The blue line is the average d-bias lasso. And we see that even though the number of data points on each machine is the same, I'm taking advantage of the net. I'm taking advantage of the total number of data points. The error is going down. And on both these two simulations, I have a slightly different covariance structure of the predictors. That's what the two plot. Yes?
So why couldn't I just do least squares using your cool generalized inverse? The generalized inverse, your cool, that cool one you got, and then and just use least squares. Why am I doing lasso at the lower level anyway? I mean, it seems to me I could just. It just seems, yeah, I could probably say.
That's a very good question. I don't know the answer off the top of my head.
I'd love to see what would happen.
I'll have to think a little bit harder about that. But my hunch is because if I think about this inverse in some sort of a generalized sense, this would be the pseudo inverse. This gives me the minimum L1, L2 norm solution.
Yeah.
And what I'm really looking for here is the minimum L1 norm solution. So these two things might be very different. So yes, in that case, you will get no bias. You will get your averaging would successfully reduce the variance, but this average will converge to, in some sense, the minimum L2 norm solution, not the sparse solution that I'm looking for.
Even though you sparsify it afterwards.
If I sparsify afterwards, I might end up killing completely the wrong components because again, it's converging to something else that might have a completely different set of large and small components. That would be my intuition, but I don't have any math to back that statement up. Okay. So anyways, this approach works. It's taking advantage of the net total number of data points. But there's a catch, is that this estimator is usually not sparse. And we want a sparse estimate. We want a sparse estimate. A theoretical reason for wanting a sparse estimate is that this I was looking at L infinity entry-wise error. If I were to look at L2 error, L1 error, then this estimator might do very poorly because it's completely dense compared to the truth. And that is true. So what we're going to do is we're going to high threshold. We're going to set all the small entries to 0. It turns out if you do this, you can show basic consistency in both the L2 and L1 norm. And for those of you who are familiar with the theory of the lasso, you notice that these are exactly the rates of convergence for the lasso. That means that if you were to somehow manage to buy a giant computer and solve the lasso on the whole data set, or say run it with some distributed optimization algorithm, you would expect comparable levels of error versus this estimator. Yes?
The L infinity norm is only applies to this particular segment of the codon structure, correct?
Say it again?
So the L infinity norm bounds only applies to this particular design matrix we consider. Because in general, you cannot derive by under arbitrary
So
integers.
it's okay for a general, so it doesn't really, so the constant in front would depend on the covariance structure of the predictors, but the rate does not. The rate is always log p over n. It depends on p and n are listed there. You're correct that the constant in front depends on the
My
covariance structure.
understanding was only under the so-called very strict pairwise incoherence conditions, this can be derived.
Oh, so you are correct. There is the dependency there is a little subtle. The dependency is there that the incoherence parameter will show up as a constant in front of the bias term. Okay, so the more incoherent you are, the less incoherent you are, the bigger the bias term will be, and the more number of points you have to keep on each machine. But as long as that happens, as long as you keep enough points on each machine, you can always make it small enough.
But S squared log.
Yes.
Okay,
Yes.
I got you. Thank you.
Yes. So anyways, you can verify, and an interesting corollary for this L infinity error bounds is that you can get model selection consistency. What I mean by that is I can make sure that the support of my average hard threshold estimator is exactly the same as that of the true parameter vector. And again, for those of you who are familiar with your lasso, I may know your representable assumption here. Okay, so let's kind of look at this in simulation. Like I kind of alluded to, the D-bias estimator without high threshold, the completely dense one, does very poorly in L2 error. But once I threshold, I see I'm doing comparable to the lasso estimator. And this is again 2 different covariance structure for the predictors. Yes.
So wondering about the gaming computation you said about earlier, what would be the optimal choice of hand
So
in terms of both computation and still maintaining the statistical band?
yes, so that's an interesting question. There's a trade-off there. So essentially what you will see is that as you slowly crank M up, if I fix the total number of data points and I kind of crank M up, divide it more ways to take advantage of having more machines, I will see basically the error staying constant. I've actually applied the end. I'll show you at the end, but you will essentially see that the error stays constant until you split the data 2 many ways. And then you will see the error start to grow. Okay?
There's a threshold.
Yes, there's a threshold. Basically when M gets bigger than this type of thing. When that condition becomes violated, error goes up. You will see.
In terms of computation?
So in terms of computation, it's quite hard to quantify because if you think only in terms of communication costs, then of course having more machine will cost you more communication. But the lasso problem on each machine is getting smaller number of data points, so those are getting faster. I don't have a quantitative statement to quantify that trade-off, but that would be the 2 things that are at play over here. Okay. Yes.
A little bit in the same direction with the question. So how are you gaining compared to a scheme in which I will just use the data that I have, capture every data set that I have, and write the lasso problem with those capture every data set and solve that perhaps using some of the schemes. I guess here if you use all of them, you get pretty big matrix, right? That might sort of cost you the computational to
Yes.
But I guess there are some of the schemes that you can do even taking advantage of the cost that you pay.
Yes.
So do you have any insight into when something like that, when what you're doing here will be better than an approach where you try to do?
Sure. The one sentence answer to that question is when communication is much more expensive relative to flops. So in some sense, we've kind of optimized this algorithm to minimize communication without regard for the number of floating point operations I have to do. And so since I'm optimizing in this setting, when my computational setup actually fits this bill, this algorithm would do very well. Now, say you were to do this on a single machine, this is just some multi-core stuff and communication wasn't really that expensive, then you should solve the last one. Because it will be communication-wise more efficient. But statistically, they're the same. That's kind of the point I'm trying to make. You get similar error guarantees and rates of convergence. Yeah, sure.
So my understanding this way, you split our data to M machines or smaller, and then each one takes smaller time, but the overall sum across machines of the complexity sum out to be exactly the same as if you solve the muscle in one single processor.
So that's almost correct, except that this debiasing step is actually quite expensive if you think about it. If you think about what the debiasing step is doing, I have to solve basically P-lasso problems. This is essentially P-lasso problems. Okay? So the debiasing step can get kind of expensive. And this is where the trade-off between communication comes, because it does require communication to debug. Okay? But in pure number of flops, it's a little expensive. But I'm not sure how many of you are in numerical analysis, but they're kind of the same in numerical analysis these days as flops are free. Okay? So there's a strong kind of push towards minimizing communication. And so that's why we've kind of decided to do this algorithm in this setting. Now, I will briefly mention that. I've only kind of alluded to the tip of the iceberg. Okay? This is not the only way. Sorry. This algorithm is not the only way of doing this. There are algorithms that will allow you to amortize this cost of debiasing across the whole cluster. Okay? There are algorithms that, I'm not going to tell you exactly what it is because the algorithm is a little complicated right now. The algorithm requires 2 rounds of communication. But there are other ways you can do this based on this debiasing idea. Okay? And if the flops do become a concern for you, you can, tune a knot along this trade-off. Okay? I will leave it at that. Now, I'll be happy to chat with you more about that later. Okay. Where was I? Okay. So I've kind of, you guys asked questions at the right time. I'm kind of done with this section. So I will just hint at some other extra work, okay? So this actually doesn't just work for sparse regression. You can do this to any kind of structured estimate generated by an M estimator, okay? You can, I'm not going to tell you the details of how to do it, but you can apply this idea to that setting, okay? So it's a lot more general. Not just sparsity, and not just linear regression. The second thing is, we are working with the company in San Francisco called Adroll to run some giant logistic regression data set with this algorithm. And what they have is, right now they use L2 regularization, and the reason they tell me is we have not been able to run L1 before. And so we're hoping that with this approach that it will allow them to use L1 at least, and maybe not put in practice, maybe L2 would just do better, but at least allow them to look at that possibility. Okay, and we're, this company, this is private data, so we don't have it. We're waiting on them and they also have to make money instead of just coding up our algorithm. So we're waiting on for some results of that. Okay, so to kind of summarize, can you do distributed sparse regression with one round of communication? Okay, the answer is yes. Okay, the answer is yes. What you're going to do is you're going to average debias lassos. The nice thing is that it converges to the same way as the centralized lasso. Okay, you get the same error guarantees if you were to manage to somehow solve this giant lasso problem. is model selection consistent? Okay, without the irrepresentative assumption, there are some catches that if you're interested, I'll tell you more about it. And all this is true as long as you don't split the data too many ways. All this is true as long as you don't split the data too many ways. Okay. So that was the first part. That was some distributed estimation. Okay. Now let's talk about the second thing. The second thing is inference. Inference for the selected coefficient. So this problem is in some sense a little bit more general than just inference for the selected coefficient of sparse regression. This is in some sense inference after model selection. And this is a problem that really arises out of a discrepancy between the statistical theory and statistical practice. So in theory, when we prove theorems, we think, okay, the user, or the practitioner has a model a priori fixed. Then he's going to go collect some data and then do inference with the data. But in practice, those first two steps are kind of flipped. Okay, what they're going to do is they're going to collect the data, and they really have no idea what model to fit. So they're going to use the data to inform their choice of a model, and then they're going to do inference. And they're going to perform inference pretending that they had in fact chosen the model before collecting the data. Okay. And let's ask the question then, because are these inferences valid? And unfortunately, the answer is no. Okay. And this is kind of no. There's a lot of work going back. Various forms of this problem, but the basic intuition is basically this adding this model selection step in the middle here kind of distorts the distribution of your statistics post-selection. Okay, and that's really why everything breaks. I'll show you an example. Very simple example. Standard linear model. I have predictors, actually Gaussian errors. Okay, the x's are correlated here. The x's I'm using are correlated. This is the procedure that we're going to use is I have two predictors, x1 and x2. I'm interested in the effect of x1, say it's some treatment I'm interested in. And I don't really know if I should account for the effect of x2. Okay. So what I'm going to do is I'm going to fit the full model, x1 and x2. I'm going to test for the significance of beta 2. If the test rejects that beta 2 is significant, I use the full model. If the test accepts, then I'm going to throw away predictor 2 and only use the first predictor. Very simple setup. And then I'm going to form confidence intervals based on my estimate, my point estimate for beta 1 and the standard error. So both these quantities depend on the model that I chose. That's why it's indexed by mHat, the randomly selected model. Okay, so I'm just going to form these intervals. I'm going to repeat this procedure, this whole procedure, including the testing, okay, multiple times. I'm just going to look at what kind of frequency properties I'm going to expect out of these confidence intervals. Now, if you think back to what the frequency properties of this interval depends on, it depends on the Gaussianity of a certain pivot, particularly this pivot. Okay, that thing should be normal 0 of 1. But it's not normal 0, 1 the same. My pivot is not normal 0, 1. Red is normal 0, 1, blue is the empirical distribution. It's quite far from normal 0, 1. The coverage in this case is about 60%. And there are examples that I can give you if you're interested that I can drive this coverage probability to 0. Okay? So it's not just a small problem, it's a real problem. Okay, so here, that's the problem. Now what are we going to do? I don't like to keep the audience waiting, so I'm going to tell you exactly what we're going to do. Okay? What we're going to do is instead of, so we're only going to look at this problem in the context of forming confidence intervals. There's an analogous story for hypothesis testing, but I'm not going to get to that. Feel free to ask me about that later. I'm going to, if you think about what a confidence interval is, it's a function, right? Eats in data and spits out an interval. I'm going to make one of these functions. I'm going to make one of these intervals for every model that I can possibly select. Okay? For each model that I have possibly select, I'm going to have such a function, such an interval. Now, what kind of coverage probability, what kind of frequency properties do I want? I'm going to require that the interval for model n, conditional on the model selector spitting out model n, has the correct coverage probabilities. Okay, this is the kind of coverage probability that I'm going to require. And this is really the key idea here. This is the main idea, is to require inferences that have valid frequency properties conditioned on the selected model. Okay, this is the main idea. Why? Well, one justification is this gives you certain unconditional coverage probabilities. That is a very simple calculation. The kind of the meta procedure of looking at which model was selected and then applying the correct interval gets you valid unconditional coverage probabilities. Okay, that's one way to do this. So this is the key idea. Are there any questions about this? You look like you had a question, Ben?
Yeah,
Yeah?
so there you have an M in the subscript of the confidence interval thing.
Yes.
So does that mean that if I,
So confidence interval is a function, eats in data, spits out an interval. I'm going to have one of these functions for every possible m. So if I see a different m, I'm going to apply a different function to my data to get an interval. Which function I apply depends on the outcome of the selection step, which I observe.
yeah, so your conditioning statement is that that model was selected, not that it's the correct model. That's why.
No, I have made no assumption that it's a correct model.
And obviously, this
Yes.
depends on your algorithm for selecting models. You will have
Yes.
performance differences basically between.
Of course, yes.
models.
But the idea is this is a framework.
Right, sure.
Okay for any model selection, sure,
Sure.
almost any. But we'll get to that in a bit. Okay?
On J,
Yes.
statement.
Yeah, otherwise it sort of doesn't make sense. It's like, if I choose a model and it doesn't contain the J predictor, I want to make a confidence interval for it. I mean, it sort of doesn't make sense. You can do that,
So
but
then
it
does
sort of
this
doesn't
sum,
make sense.
does this sum as a criterion, does it make sense? Because if 99% of the models are wrong models, and then there's 1% of the models which has this, say, has a set of 2 coordinates, and you give them equal weights, how does that,
I
does
will-
that help us?
I will address that concern in a few slides, okay? I will address that concern in a few slides. Hold the question. Any other questions? Oh, okay. You're just scratching your nose. Okay, so here's the setup that we're going to talk about. It's sparse regression again. Okay, remember, I'm setting this whole thing in the context of sparse regression. So here's the setup. I have y is the data. Okay, I'm thinking of x as fixed now. X is no longer x is a fixed design matrix. Y is the data, and it is generated according. It's Gaussian. Okay, with some mean. We create this mean is the conditional expectation of y, given x if you want to think about x as random. Now, x is a set of possible predictors, and we're assuming that the model can be misspecified, so x may have nothing to do with the conditional expectation of y. Okay, and this kind of answers your question. We don't have to assume a correct model. Now, if you want to assume a correct model, we can chat more about that. But in this talk, at least, we don't assume any model is particularly correct. Okay, this is the setup. So, and we assume that the variance is known for now. Okay? In this setting, what is least squares estimate? I don't have a true parameter. What am I trying to estimate? Well, if you think about the least squares objective function as simply an empirical version of this population objective function, then you see that least squares is trying to estimate the best linear predictor to the y's in terms of the x's that you were given. In other words, it's trying to estimate the best linear approximation to the conditional expectation given the predictors x, okay, this set that you were handed. The key thing to take away is that these targets are linear functions of mu, this conditional expectation. In particular, each regression coefficient is given by just one row of the pseudo-inverse of x times mu. Linear functions, okay, linear functions. Keep this in mind. So let's add model selection. This is kind of the setup that we're interested in. I'm going to do selection, and then I'm going to do estimation. Okay, I'm going to select the model, I'm going to fit the selected model. What is this estimating? What is this estimating? This is just estimating the best linear predictor in the context of the selected model. Okay, in the context of the selected model. Again, these are all linear functions of the conditional expectation. They're random linear functions, right? Because which linear function I apply depends on the outcome of the model selection step. But they're nevertheless linear functions. If you are uncomfortable with the idea of a random target, okay, think about it like this. Consider all possible models that you can select, all 2 of the P possible subsets of P, okay? In each of these subsets, okay, there is a target, because the target now depends on the model. So for a predictor, okay, for all the models that it's in, you have a target that's well defined like this. And now you have this giant list of targets, very, very long vector of targets. And what you're doing, you're simply picking subsets of this to do inference on. Okay? So yes, they are random, but there is a population level quantity that you're essentially doing selective inference on. This is how you should think about it if you're uncomfortable with the idea of random targets. But the point, anyways, however you choose to think about it, the point is I'm doing inference for random linear functions of the conditional expectation, of the expectation of y. Okay? This is the goal. And here's kind of an example where you would do this. This is an HIV data set. Simply fitting ordering these squares gets you regression coefficients that look like this. So the x-axis is the individual predictors. The font is deliberately small. It doesn't really matter what they are. And on the y-axis, I'm plotting basically the size and signs, the magnitude of each of the regression coefficients. A lot of them are small. So I might think that some of these are actually secretly irrelevant. So I'm going to do model selection and say I'm going to fit it with the lasso. Okay? Fit the lasso and look at the active variables. And then I'm going to use, only going to use lasso as a model selection set. Look at the lasso that model selection. I'm going to refit these squares on this set of selected predictors. And the lasso selected coefficients given in blue, and the refit at these squares coefficients are the black dots. Okay? Just an example where you want to consider a set like this. For sure, you don't believe the linear model here. I mean, I don't believe the linear model. Why would HIV drug resistance just be dependent linearly on this bunch of genes? Okay? But I might want to do model selection because the effects are, a lot of them might be small, or perhaps actually relevant. Anyways, this is an example that showcases the applicability of kind of this framework that we're going to work under. Now to the framework. Recall the goal is inference from random linear functions of the expected value of y. Random linear functions and mu. And my goal, remember, my key idea that I talked about at the very beginning was I'm going to find conditionally valid intervals. I'm going to make one confidence interval for each of the possible models that I may select. How exactly I'm going to do this? I'm going to derive a pivot, okay? I'm going to derive a pivot for each of the possible models that I can select, okay? And when I invert the pivot, I'm going to get a confidence interval. Because each of these pivots are, well, in this case, they're uniform, conditional on the model that is selected, the confidence interval will have the corresponding conditional coverage frequency. Yes?
How is this possible if you don't have information about your model selection rule and path?
Oh, of course. We need information.
So,
And that information will come up in a little bit.
okay.
I'll show you how it enters.
Okay, sure.
Any other questions about this pivot? So this is how we go do a hypothesis test. I mean, this pivot is uniformly distributed on this one, and also this is just a p-value. So you can do a hypothesis test with this, but that's all I'm going to say about hypothesis testing. Okay. So the key is now this pivot, okay? And your question is, the answer to your question is coming up, okay? Let's look at the event that we're conditioning on, okay? The model selector selecting a particular model. Now, if you think about the model selector as a function, right? What does it do? Eats in data and spits out a model. Let's say that now there's a finite set of possible models. In all practical scenarios, there's a finite set of possible models. Now, what this is going to do is you can consider the set of data that generates a particular model, the pre-image of a model, so to speak, under this mapping, under this model selector. This is just a region of Rn, right, which is where the data is called. So conditioning on the model selector, picking a model, is equivalent to conditioning on the data falling in some subset of Rn. Okay? In particular, falling in its pre-image. Right? And it's a partition of Rn. The key that we're going to explore is that in a lot of these cases, we can kind of characterize this region very nicely. In fact, they're polytopes. And you can characterize them by a sequence of linear inequalities. Okay? I'll show you how to do this for a particular model selector, namely the lasso in a little bit. But the key is conditioning on a particular model is equivalent to conditioning on Y falling in a polytope. Okay? This is the takeaway message from this slide. Here's a picture of what these look like. So here are the lasso selection regions. These are all polytopes, and Y falling here means a model, Y falling here means a different model, so on and so forth. Okay. So I'm telling you about this pivot. What is this pivot? Well, this is what it is. And, this function is a truncated over CDF, and you got these truncation limits. But the point is, you can write this out. This is an explicit form for this pivot. The details are not really that important. But if you notice, what I have is I have a function, okay, of my statistic, such that conditioning on this data falling in a polytope is uniformly distributed. This function is going to be that pivot. Exactly what it is, not too important. There's geometric intuition. I'm not going to talk about, here's the geometric intuition. But you're going to ask me later.
Yeah, so a natural thing is to ask, so in general, you're not going to have normal data. So I'm sure you have thought about how you would use this pivot as an intuitive starting point in a more general setting where you don't really know the error and you're going to depend on large samples, whatever large means, I'm not quite sure. But have you
Yes.
thought about that?
We have thought about that, and I'll get to that at the end when I
Oh,
talk
great.
about extensions.
Yeah,
But
okay.
let's stick with the normality for now.
Okay, okay.
Yeah, I like that sense. Okay. Anyways, so this is just a restatement of what I just told you. The corollary is that conditional on a particular model being selected, if I can characterize this event with a set of linear inequalities, this is a pivot. This ugly function is uniformly distributed. Okay, this is going to be my pivot. Okay. Following the framework, how I'm going to get intervals? I'm going to invert the pivot. Okay, I'm inverting the pivot to get intervals. Now, what kind of coverage probabilities do these intervals have? Well, these pivots are conditionally valid, so these intervals, of course, are conditionally valid. But again, the meta procedure of looking at which thing the model selected output and applying the correct confidence interval has unconditional coverage probabilities. Therefore, if you're uncomfortable with this conditional frequency property, just keep in mind, these things behave exactly like confidence intervals that you're used to. Okay, you have unconditional coverage probabilities. There's nothing funny about these frequency properties listed down here. Yes, Ben?
So beta star sub j comma m hat, that's the target
Within the model that you selected, M hat.
within the model that I selected m hat. So having selected that model, this is the regression coefficient node conditional on that selection. So it could be different for a different selected model.
Yes. So to answer your question, to maybe assuage your little fears, you can have them all the same. I mean, these are just linear functions. I'm making a confidence interval for linear functions of u. I can pick them to be all the same. They don't have to depend on the selection event. Then I'll be making them all for the same target. Sorry, Shana.
I'm confused. I think next question is regarding beta star.
Yeah, beta star is the target. So
Yeah.
beta hat is like the estimate of the target.
So beta star actually changes?
Beta star can change depending on the model that you select. It can change.
Beta star was just
Because I'm in this completely misspecified model set, where the thing that linear regression is estimating is I'm thinking of as the best linear predictor within that model. So of course, if I choose a different model, I'm estimating something different.
So beta star is an oracle in that selected model and hat, which
Yes.
is start to the OLS.
You can think about it like that. Yes. Yes. Yes.
I think
Yes, Ben.
maybe I want to give you a chance to finish your talk, but it's an interesting notion. I'd like to, maybe we can discuss later.
We can chat more, but this is not the only targets that you can make confidence intervals for. You can make it for any linear function. So for example, I can always, if I assume that the full model contains everything that I want,
Yeah.
I can always make it simply a row of the full predictor matrix. Theta be a row of the pseudo-inverse of the full predictor matrix. Then I'll be making confidence intervals for the same target regardless of the models I choose.
Uh-huh.
It's a framework. I
Can you
don't
just
have to
say
be
that
making
again?
confidence.
Can you just say that again?
Sorry.
Say that again. Which
Okay. No. Okay. So what I can do is actually I have a slide at the end on this. It's sort of close to the end. Okay. So for those of you who are worried about this target, there are other targets that I can consider. Okay. For example, I want to make confidence intervals for the truth. Okay. There is a way to do this. This is what this theorem is trying to say. Say I don't believe in the linear model, but I believe I've accounted for everything that could possibly affect this target. So I believe my predictor X has everything in it, and that's the correct model, but I just don't believe in the linear relationship. Okay? So now what I can do is I can make confidence intervals for the targets in the context of the full model. Right? My target's beta star is just given by the full X dagger pseudo-inverse times mu. This set of targets does not depend on the model being selected. So every time I can make intervals of these. This is just another linear function of mu. And this doesn't depend on the selected model. Okay? This doesn't depend on the selected
Does it depend
Yeah.
on P?
Well, yeah, this depends on, in some sense, you're believing that the full model is valid. So in some sense, it depends on, well, it depends on the full model, so it depends on the size of the full model.
Right, but the model size is increasing with the sample size.
Oh, you're talking about this particular statement. Is that what you're talking about?
No, still trying to understand your argument that you have a fixed quantity of interest, but here I don't think it's fixed because it's also changing with p.
We're thinking that the predictor matrix is fixed. You're considering x as fixed. This is fixed design.
Oh, so this is a fixed.
This is
But
fixed
the dimension
design.
of x is also fixed.
Well, if x is fixed, then we're not growing x.
Oh.
X is just handed to you. It's a fixed matrix of predictors of covariance.
Okay, I'm a little confused. I thought that the dimension of the number of covariates could increase with sample size.
So this framework is agnostic based on that. So all the results don't depend on p. I mean, it's really for the assumptions on x are very light. It's that you can't have like 2 duplicate rows. Basically, the columns of x are in general position. That's the assumptions on x. Anyways, no. So all y'all have questions. Let me finish. Almost done. Almost done. Okay. Where were we? Here. Okay. So I'm going to show you real quick, maybe an example will help. Okay, an example. Actually, context of your question. But let's do this example. So let's consider lasso as a model selector. Okay. Lasso eats in data and spits out a set of active coefficients. For convenient purposes, and you'll see why this in a couple of slides, I'm going to use a finer selection event. Instead of just conditioning on lasso selecting a particular set of active variables, I'm also going to condition on the signs of their regression coefficients, which is just a finer selection event. And you'll see why I do this in a couple of slides. You can characterize this, so, okay, this is a picture of the lasso selection region. I kind of lied in a couple of slides ago. Each of these regions really does not correspond to a particular set of active variables. It corresponds to a particular set of active variables and a set of signs with the coefficients, okay? And you'll see, okay, so this event, I can characterize it by a sequence of linear inequalities. Again, the details are not important, but there is a set of linear inequalities characterizing this event. Lasso choosing a particular model and a particular set of signs for their coefficients corresponds to y following this ugly polytope, okay? And this is the polytope that's plotted. This is the polytope that's plotted. So this is, if y found here, lasso would choose variables 3, variables 1, and give them both positive signs.
And by saying
Yes.
lasso, you have a particular way of choosing lambda that's also data-driven or something?
Lambda is fixed here.
Ah, okay.
Lambda is fixed. I think I forgot to
Sure.
say, but lambda is fixed.
Oh, sorry.
Not chosen in a data-dependent
Okay.
manner.
Oh, okay.
We can get into extensions on that. Sorry, is there? So.
No, it will be too much. Just having everything data-driven. Yes.
Yeah. You can do that. You just have to condition the choice of lambda.
Sure.
But anyway, we're not getting into that. This is okay. So finally, recall we're making intervals, right? How do you invert this pivot? I need to do this to get my intervals. This is actually turned out to be relatively easy because this function is monotone the argument they're trying to invert for. So to get this interval, you solve 2 one-dimensional monotone root finding problems. Okay. So it's really not hard. It's one-dimensional. Okay. The continuing example on the HIV data set, there are a couple of interests. So that in that case, we actually ended up selecting 10 variables. And here I'm showing the naive coefficients. We're just plotting down plus minus 2 standard errors and what this approach would have given you. Okay. The model selector here is the lasso. I want to point out a couple of things. First, you can get qualitatively different results. Okay, I think everybody shows you this kind of a thing where something is significant naively, but not significant if you do it correctly. But another thing I wanted to point out is that these intervals can actually be much wider. Okay, if you look at the naive interval and compare it to the length of the exact interval, the interval is much longer. Much longer. Okay. Just telling you that this can happen. Why really? Why? Intuitively, it's because this variable barely entered the lasso model at that value of lambda. Okay? Lasso is still kind of unsure whether to enter, basically. And so conditioning on the fact that it entered really discards all the information that we have about this variable. And so intervals are very long. Intuitively, that's what's going on. Okay. To conclude, and to get to some of your questions maybe, this is a framework. This is a framework based on the idea of conditioning on the selection event. You can do this for all kinds of other model stuff. You can do this for, well, all these things. I will point out 2 significant extensions. One is, if you want to do it for Fourier stepwise, the selection regions turn out to not be defined by linear, rather they're defined by quadratic inequalities. And so there's some technical hurdles that need to be overcome there, but you can do it. I also mentioned that sigma is known, okay? But you can, again, use a different model selector that is pivotal with respect to sigma. For example, the square root lasso. This will take care of the unknown sigma case. You can also do other kind of statistical models. Okay? You can do sensor regression problems. You can generalize the data to be from any exponential family. This leads to computational type problems. This may lead to computational problems, but at least theoretically, everything falls through. Okay? And finally, you can also do non-Gaussian errors that some heavy tails in some way. Again, yeah, you are correct, and this is via an appeal to asymptotics. For example, this will allow you to handle GLMs, where the score, the sufficient statistic is what's important, and that asymptotic can be Gaussian. Looking at least. Okay. So to wrap up, in summary, the goal, we call it, is inference for random linear functions of the mean. The idea is to find conditional pivots. Okay? Pivots that are valid conditionally on the selection event. And you get selective coverage, and you also get unconditional coverage. So you can think about these confidence intervals, despite their additional selective frequency properties, as perfectly valid confidence intervals in the usual comfortable, if you will, sense. Okay? Okay, that's it. You guys can ask me all the questions.
Any remaining burning questions? Maybe Nancy didn't get a chance.
Okay. All these things sort of rested on you can build this pivot and you will reach this uniform field one condition one.
Yeah.
But it was working on this complex mu, but I can see your random target. Right? So in order to say mu can be anything, my question is actually very simple. Because in real life, if you have a very complex function, you have very large p, there's no way you can estimate mu. So
yes.
Is it so general that you can say, this will apply to very general mu, or in practice, is there any way you can check is your pivot condition or is it violated?
So the pivot is what's actually much more of a problem with the Gaussianity assumption. The mu, it doesn't really depend on mu, because we're making inference on linear functions of mu, and so the pivot only depends on mu.
I need to look into the detail. I don't believe, so you have for example, very chaotic mu, I don't think the connection might be work for that. Very chaotic mu, are you sure you can still build this pivot, which is still uniform, reaching this uniform?
So you can build a pivot. The key thing is that if mu is completely unrelated to your x, say, maybe, then these targets would maybe have almost nothing to do with what you think are the regression coefficients.
So you don't even need any kind of smooth or...
There's no smoothness assumption of mu. Yes. There are other catches, so let's put it this way. Your targets may have nothing to do with what you think you're doing inference for. And the other catch is really the Gaussianity assumption is quite crucial. So the asymptotics the assumptions that are to make for the asymptotics to go through are quite strong.
So distributional assumption is more important to this
Yes,
framework
it's
than
extremely
this
important. Yes.
Okay, thank you.
Yes. Sorry, more questions. Hi, Ben.
Me again. Sorry.
Then you take one more.
Oh, sorry.
Yeah, then I have to shut up. I think that, so let me clarify the worry that I had, because it may be that I would just need to think it through and you can help me think it through, and then it immediately goes away. But if not, I think it sort of relates to Nicen's question. So my worry about the conditional criterion is, suppose that the true model has the property that models unlike it tend to get selected. Now, the conditional coverage criterion that you have on the board, it evaluates, the confidence, the interval that's reported for a coefficient is evaluated in terms of whether it covers this other regression coefficient, other than the one in the true model. And if it is the case that you're selecting a model that's importantly different from the true model, it seems like the coverage criterion is doing something funny. And I would think that this issue of chaotic mu's might bring that problem to the fore, perhaps by increasing the likelihood that you would start selecting models that are in the relevant ways unlike the true and correct model.
So you are correct in pointing out that sometimes when you believe in the linear model, okay, these targets don't make sense. that instead you want to perform regression on this truth, this generative beta. I have two answers to the question. The first is, I think in a lot of cases, you don't really know if the linear model is true. But that's kind of a cop-out answer. So I'll tell you what happens when the linear model is true. You really want it confidence intervals for, what is that slide? Yes. Then you really want a confidence interval for the true generative regression coefficient. So in the low-dimensional setting, this is just a linear function of the mutes, given by the correct pseudo-inverse. In the high-dimensional setting, this is unfortunately not a linear function. Okay, but what we can do is approximate it. Okay, and we can approximate it quite well because we can approximate it to within an error that decays like 1/n, versus confidence where usually the width is 1/√10. Okay, so you get some kind of asymptotic coverage of the true regression coefficients if you truly believe the linear model. Under some more assumptions. I mean, there are assumptions that require basically consistency of the lasso. You need to make some assumption of the sign matrix, again, type incoherence type assumptions. But under assumptions, basically that high-dimensional regression is consistent. This will give you coverage in the high-dimensional regression setting. Hopefully that addresses your question.
I think that it sort of satisfies me about what this is saying about your method. I still kind of have to scratch my head and think a little bit about the sort of general definition of that you're working on of conditional coverage.
Yes.
But I find it satisfying.
The takeaway message is really that this is a framework. Okay, you can cover whatever target you want as long as the linear function of mu. So whatever regression coefficient suits your fancy, cover that target.
Okay, one last question.
I'm sorry.
Take it offline then.
Okay.
Even though I'm sitting in front of Ben, I'm way behind him. What is it that has to fall in the yellow polytope? Is it mu or y?
Y.
Y falls in yellow polytope.
Y.
Thank you.
Yes.
So it's general in the sense that I have to have some idea of how these regions look like, right?
You need to be, that depends on the model
selection,
selector,
right?
and you need to be able to characterize them. Yes. I think she had a question. That's the last one.
Quick one?
Yeah.
One quick.
So I feel this is about to shift the target like million.
Yes.
So my question is there any way you can use the L2 or L1 consistent results to create this gap between the shifting target versus original target?
Yes.
How to adjust the confidence intervals?
So the reason we shifted the target was because I don't believe in the validity of the linear model.
Sure.
But if you were willing to believe, then this is the theorem that you're looking for.
Yeah.
Is that this target, this thing, I mean, this is it's an affine function of mu, but the affine term is fixed, conditional on the x's and conditional on the model that you select. So this target is a good approximation to the generative beta naught coefficients, okay? And this is where the high dimensional consistency result, because the assumptions for this is precisely high dimensional consistency of linear regression. So that's the connection.
So you guys think that's sufficient? That's sufficient to be sure to give people the kind of reassurance they need.
It gets you asymptotic coverage, which is the same that any of these other approaches can guarantee anyways.
How about the non-components?
Yeah, we're working on that. Yeah.
Thank you.
So.
All right. Well, let's thank you guys once again.